Hello there guys, how's it going? Mike coming back at you here with another video on vector calculus. In the previous video, we did several sample problems using the divergence theorem, and we talked about the relationships between some of the theorems that we had learned about earlier on in this course. In this video, we are going to begin to get into the thing that ties all these theorems together. We're going to get into differential forms. And what we're going to talk about specifically in this video is why do we need these things called differential forms, and just a basic introduction into what are they. So if you think back to the end of the previous video, as we said, we saw that the FTC, the flux divergence form of Green's theorem, and the divergence theorem are all saying the same thing, just in different dimensions. We also saw that the circulation curl form of Green's theorem and Stokes' theorem are saying their own same thing. And then we saw that the circulation curl form of Green's theorem is essentially the same thing as the flux divergence form of Green's theorem. And when I say essentially it's the same thing, I mean you can take the flux integral in the flux divergence form, do a little bit of renaming things in terms of P and Q, and then apply the circulation curl form of Green's theorem, and you get the desired result. So really those two things are stemming from that same thing. So what this is saying is that all these theorems are really all tied in with each other. All these theorems are in either R, R2, or R3. So the fact that we can get all these big theorems to all be tied into each other up through R3 suggests that maybe these things go up even higher. And there's a general theorem or general formula that all these guys which we learn about are just special cases of. Well, the problem is the tools that we've worked with so far, that is to say vectors, they sort of limit us. For example, when it comes to curl, the curl is only truly something you can find when you are in R3. Yes, we worked with the K component of our curl, which lies in the XY plane when we talked about Green's theorem, but the curl, the full-on curl, is something we can really only find in R3. There's no real concept of curl in R4 or R5 or even higher. There is a notion of the divergence of a vector field from, say, R4 to R4, R5 to R5, and so on and so forth going up. So we may be tempted to think that we can somehow use the divergence to sort of generalize all these results. But just comparing the divergence theorem and Stokes' theorem, we're working with two totally separate seeming things. The divergence is the dot product of del and our vector field. The curl of our vector field is the cross product of del and our vector field. One of these things is a scalar quantity. The other one is a vector quantity. Two separate things. So they're not really that tied in with each other, or at least not tied in enough to really suit our purpose. So vectors really only get us so far. It doesn't quite get us all the way there. We can't generalize these big theorems just through the use of vectors. Now, some of you may be wondering, can we actually generalize these things? Can I take the divergence theorem and Stokes' theorem and raise these things up to even higher dimensions? Because just based on the sounds of these theorems, I'm not so sure it's possible. Well, let me put these theorems into English. What these theorems are saying is that the integral of some component of your vector field, in the case of the divergence theorem, it's the integral of the normal component of your vector field. In the case of Stokes' theorem, it's the integral of the tangential component of your vector field. But the integral of some component of a vector field over the boundary of a region equals the integral of some kind of derivative or some component of it of the vector field over the interior of that boundary, over the region itself. We know that from Stokes' theorem, we were integrating the normal component of our curl. In the divergence theorem, we were just straight up integrating the divergence. So there is some kind of a derivative going on somewhere here. Hearing these theorems stated in this sense, these theorems do sound similar enough that we should be able to say both of these things in one unified kind of concept. We should be able to come up with something that will incorporate both of these kinds of theorems. And these are where the differential forms come in. We need these things called differential forms to be able to write all these theorems that we have seen up until this point as one big main theorem. Now, as I said, we're going to give a solid introduction into differential forms in this video, and they're used pertaining to these theorems only. In the general world of differential forms, you can have these differential forms in R4, R5, all the way up, and in other vector spaces, we're only going to go up to R3. So suppose we have an open subset of R3. We're going to call this open set K. A zero form on K, or a differential zero form on K, is simply a real valued function that goes from K to R. So this is like any calculus 1, I shouldn't say a calculus 1 type function, but a single variable function or a multi-variable function, say f of x, y, z. Typically, for the most part, that's what we are going to see, but it could be just a function of x, it could be a function of x and y, or it could be a function of x, y, and z. So if we have two differential zero forms, f and g, on this set K, we can add them to get the zero form f plus g, or we can multiply them to get the zero form f times g. And this is just basic adding and multiplying of functions, just like we would do it any other way. So I have a sample here, f of x, y, z, e to the x plus sine y plus cosine z, g of x, y, z, x, y squared, z cubed. We add them in the typical way. We multiply them in the typical way as well. So real valued functions are differential zero forms. A differential one form, or just a one form on K, is anything that's of the form, now that is an omega there, not a w. So omega, some function p of xyz dx plus q of xyz dy plus r of xyz dz. Or for short, as you'll see it written fairly often, p dx plus q dy plus r dz. And really, it's a linear combination of any of the basic one forms, dx, dy, and dz. The p, q, and r, just on their own, they are real valued functions, or they are zero forms. So if you take a real valued function, if you take a zero form, and you stick one of these dx, dy, or dz's on the end of it, it becomes a one form. Now, you don't have to have a dx, a dy, and a dz showing up in there for it to be a one form. As long as each term in your differential form has one of these guys in there, then you have a one form. So these are all examples of differential one forms. We see the first example here on the left has all three, has something times dx, plus something times dy, plus something times dz. The one below it has something times dx, plus something times dz. That's still okay. It's still a differential one form. Every one of the terms in there has a dx, a dy, or a dz attached to the end. And then our third example on the right here only has one term. It only contains a dy at the end, but it's still a differential one form. And the order in which you write the terms here does not matter. So I could have switched the first and second terms in my first example here, top left, and that would still be a differential one form. What basic operations can we do with one forms? We can add two one forms together and get a one form, or we can multiply a one form by a zero form and get another one form. So I have some samples here. I have two one forms, omega 1 and omega 2, as well as a zero form, x plus y plus z raised to the fourth. And just like in many of the problems that we've seen up until this point, we add likewise terms. We have the 3 dx in the omega 1 and the x minus 3y dx in the omega 2. So we add those guys in and we pull the dy over the dx, out. So we get 3 plus x minus 3y. And similarly for the dy and the dz. And then multiplication of a one form by a zero form works just as you would think it would. You're just going to distribute that x plus y plus z all raised to the fourth power into each of the terms in your one form. So adding and taking products of zero forms and one forms, still working in the same way as you would think. We now go on to basic two forms. The basic two forms are those dx, dy, and dz, but they're showing up in particularly ordered pairs. The basic two forms are dx, dy, dy, dz, and dz, dx. And these are expressions that should be thought of as products of our basic one forms. And be very, very careful and note the cyclic order that these things go in. It's dx times dy, dy times dz, dz times dx. You don't typically see dy dx written. You don't typically see dx dz written. You don't typically see dz dy written. We are always going to be writing these things in cyclic pairs. And we have to be picky with it because when we get to later on in the section, we're going to see that the order in which you write these things does actually matter. So these are the basic two forms. in general, a differential 2 form on our set K is any form of the form, a bit redundant there, omega equals p dx dy plus q dy dz plus r dz dx, where p, q, and r on their own are differential 0 forms on K. So if you take a 0 form, add one of these cyclic pairs onto them, you get a 2 form. Like 1 forms, the order in which you write the terms in between the plus signs does not matter. So I could have taken the q dy dz and written that before I wrote the p dx dy. It's still saying the same thing. But as we just said, the order in which you write the dx, dy, and the dz, that order does matter. Like 1 forms also, we can add 2 forms to get a 2 form, and we can multiply a 2 form by a 0 form and get another 2 form. And still, adding and multiplying works in the same way. When you're adding 2 forms, you're just going to combine like terms, if you will, and pull out the appropriate basic 2 form. When you multiply a 0 form by a 2 form, you are just going to distribute that 0 form into each term in your 2 form. And lastly, we come to the basic 3 form. There's really only one basic 3 form that there is. It's dx, dy, dz, but you can follow that cyclic order and write it in 2 other ways. You can say dy, dz, dx, or dz, dx, dy. All those guys fall in that same cyclic order. They're all talking about that same thing. Now, that's not to say that dy, dx, dz isn't a 3 form, but we're going to see how we can change this into one of our basic 3 forms. So a nice little shortcut way to figure out what kind of differential form you have is look at how many of the dx's, dy's, and dz's you have in each of your terms. If you have none of them showing up, you have a differential 0 form. If you have one of these guys showing up in each term, you have a differential 1 form. If you have 2 of these guys showing up in each thing, then you have a differential 2 form, and similarly for 3. In general, a 3 form on K is anything of the form p times dx, dy, dz, and p is a real valued function as well, or a differential 0 form. And just like 1 and 2 forms, we can add 2 3 forms to get a 3 form, or we can multiply a 3 form by a 0 form to work or to get another 3 form. And addition and multiplication, again, as you would think, work in the same kind of way. Now, when it comes to adding forms, we're never going to add 2 forms that are not the same. So we're never going to add, say, a 2 form and a 1 form. Or we're never going to add a 0 form and a 3 form. We're only going to add 2 0 forms, 2 1 forms, 2 2 forms, or 2 3 forms. It's the only way we are going to add things. We see that we can multiply 0 forms and any other form whatsoever. A bit later on in the section, we're going to learn how do we multiply, say, 1 forms and 2 forms, or how do we multiply 2 1 forms. How do we do something like that? There's a set of rules that we have when multiplying these differential forms that we have to hold to. We'll see those guys later on. So this is it for our introduction to differential forms. This is why we need these guys, and just a bit of an introduction into their general look. What form, pun, do these things take on, and then some very, very basic operations with them. In the next video, we're going to continue to work with these guys. We're going to see how can we use these guys. We're going to see that we want to look at these guys as functions, and then we're going to talk about integrals of these differential forms. And we're going to see that some of these guys look really familiar. Some of these guys give us something that look like something we've seen already. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy.